proceeds out to the city. I just want to start if you have any questions with the homework. Homework report. Okay, the deadline is Wednesday, I think, and you have quiz next Friday, right? It will be covering the first homework. So last time,
it will be covering
the first homework.
The first one.
Yeah.
The conceptual and numerical.
How's that?
And the quiz, it will be conceptual questions or numerical? Both.
Yeah. So last time, you saw that the phase equilibrium of one component, like pure component. So today we will continue with that. We use the Fugacity equation of the state for phase prediction. So we will continue with that, and we will discuss two equations that can help us do this kind of prediction. Like last, yes. The area. Then we will discuss the first and second order phase change. Then we move into fugacity, which is a helpful function that will help us do any kind of phase equilibrium, not only for one phase, for one pure component, but for multi-component systems as well. Then we will move into the Gibbs phase rule for pure component, which is simple stuff, will not take like 5 minutes. So we stopped last time with van der Waals or any kind of cubic equation of state, and it should be looking like this. And we define here, this is P set. If the area covered here is equal to the area covered here. And the way we got this, these areas is like by doing kind of tedious integration. There are two formulas for this integration. The first one is in the pressure, and the second one is in the volume. I will just do it again. PdV. It's equal to 0, and we get this one from this one. There's kind of to obtain your second homework is the kind of transformation, transform this one. Instead of doing integral in dv, it would be in dv. It's even on your second homework, I would just write it again, but I can give you like some tips. How this is done. So dv over rt, and if we did dv as dv plus dv. You can do this integration in dv instead of dv. I will write showing that again. That's dv. And this is the van der Waals. Which is the easiest cubic equation in the field. So this way, I mean, by starting with any initial guess for dv, you can start with initial guess. dv, and then solve for the zeros and choose v equal than v vector. And then you can do this kind of integral if it's 0. Then P separate as a root of prediction. So why this integral is better than this one? We have A here as explicit function of B. So it's easier to do this integral. Like just substitute B here. Take this as initial guess. For example, if water is boiling at 1 bar. This is an isotherm. We are fixing the temperature. You can guess anything and do the integral. Substitute this value, do this integral with any kind of software, calculator, anything. If this integral is 0, then this is the correct prediction of the pressure. If it's not, then repeat it with different values. Now it's not a terrible stuff because we have computers, they can do the integral for us, right? But back at days, I mean, it was hard to set an initial guess for B, and it's a tedious process. So when you think about it, I mean, you start with anything, and you do solve for BB from here, and then substitute these are your limits, and do the integral multiple times till it's 0. So now we need to find a better way for predicting the pressure, our initial guess. While this is only for cubic equation of states, because ideal gas, this is the simplest case, it cannot predict phase behavior, right? It can only be used for modeling gases, gas phases, right? The Wheeler equation of a state is a quadratic, so the stability criteria is not applied on the second part. It's like here, this is not feasible. We said the stability criteria from the second law of thermodynamics, like PV, PV should be less than 0. So this is the most suitable equation of state to predict phase behavior.
What is the first line? GC minus G?
This is G liquid phase minus G of vapor phase. I know my handwriting is terrible, but I'm trying to do my best. So now we're going to move into different models that can predict the vapor pressure. So or approximate value too. If we can predict approximate value of it, we can plug it into the equation and do the integral. It's like kind of initial guess. With like a couple of iterations, we can reach the true value. So the first equation is the Clapeyron equation, and it's based on the coexistence. This is liquid phase. This is gas phase or vapor phase, and they are different. Vapor are different. Is different from gas, right? So what's the difference between vapor and gas?
What part of the country you came from?
The density of the vapors are much more than the gas.
No. So vapor, okay, do you want?
Oh, this one's not a joke. I've always heard that it's like if something's typically a liquid at room temperature, then when it vaporizes, we call it a vapor instead of a gas. So that's what I've heard, but I don't know.
So it's the critical point. Usually you put gases, for example, nitrogen is a gas in this atmosphere because it's above its critical temperature and the critical temperature and pressure. Vapor is like it's below its critical point. So we can condense it. This is the idea of the vapor. So gas we cannot condense it ever, never. Then we change the condition to be a vapor. So we will start with the liquid vapor coexistence curve. We have here 0.1, 0.2. So we know here everything. P1, T1, we know G. G in phase 1 should be equal to G in phase 2, right? Because this is the coexistence curve. We know Gibbs is the same in both curves. So in point 2, we have T2, T2, and we have G as well. It's a new G, it's not the same G. So in the coexistence curve, we have, if we want to move DG, phase 1 should be equal to DG phase 2, right? So I will expand DG according to the formula we developed from the combined first and second law. It's VDP minus S phase 1 dt should be equal to P phase 2 dt minus S phase 2 dt. Right? No approximations, no assumptions, nothing here. So we know because they both are in the coexistence curve and they both at equilibrium. P here is the same P here, T here is the same T here. So we can dP if dP is a common factor. We can dP. So we know V phase 1 minus V phase 2 should be equal to S1 minus S phase 2. And then dv dt should be equal to, I will define given the theta I minus theta I. I will put this delta theta. Okay, so this is delta S according to this definition, not negative. This is delta S over dv. This is because we are. This is valid only in the case we are moving in the coexistence curve. This is valid only when we can also do this approximation G phase 1, which is equal to D at phase 2, equal to H minus D right, equal to H phase 2 minus D as phase 2. And they are not the same, by the way. S here is not the same S here, and H here is not the same H. And different fixes, they are not the same. This way, we can say that delta H over T equal to delta X. I'm just doing manipulation. And I will substitute the value of dH instead of ds here. So we have dV or dt, the same gives, should be equal to delta H or d. We call this like that equation. Any questions still here? Okay, this equation is not that useful. I mean, we cannot use it because delta H is function of t. You need to calculate V liquid because delta V, you need V liquid and V vapor at the same time. So not a very useful equation. And because we are engineers, we sometimes are lazy, we can do some kind of approximations. And I have another formula that can help us predict this phase transition, vapor pressure. I will erase this one. So we make no assumptions in this equation. We will make 3 assumptions and move forward. The first one is delta H is not going to change with temperature. It's fixed with temperature. Which is a very good assumption. The second one is the V liquid is smaller than V vapor by far. And this can be a good one, right? Because for you who started the homework, you can see the difference is like 4 or 5 times order of magnitude, the difference between both of them. And the third one is by the vapor phase. Is ideal gas. So now we can approximate delta V. So delta V, that now is only V vapor. And V vapor will be V or RT. This is, I said, it's ideal gas. So we can substitute for V vapor is RT over V. Right? And then in my case, this VSAT. This is not VAP. Right? So I will substitute the value of dV and the Lagrange equation. So we now have dP or dt constant gets it's equal to delta H of the vaporization, which is no function of T anymore, but T will remove this or T. for P set, and do kind of manipulation where dt, do that. This is P set. We have P set here. Go to the page, representation or P squared. What do we call this? So if we have 1 over x, we have d then x, or 1 over x dx. Right? Yeah. So we have d then x is 1 over x dx, right? This is calculus. So if 1 over p set, dp set, or dt can be d then p set, or dt is equal to delta h, factorization of p squared. And this is called factorials. Why this is helpful more than before? I can do the integration. Right? Now we can do the integration. So we have then reset d2 then reset d1 equal to integral from t1 to t2 delta h factorization for p squared dt, which should be negative delta h factorization for r 1 over t2 as 1 over t1. Sorry, this is helpful. So now if I know any point on the coexistence grid, any point, I know the vapor pressure at ADM. I do an experiment, measure the vapor pressure of any fluid like ethane, water, anything. So and then if I want to predict the vapor pressure at higher temperature or pressure, at higher temperature because I want to get the pressure, I can use this equation directly, right? At temperature vaporization at 1 atm, I can do the experiment here at these conditions. And the only thing that I'm going to change is the temperature. P set at 1 atm, I know it already. So it's easier for me now to predict or make good approximation. It's not the best, but it's the thing that we have. We can predict the value of the vapor pressure at higher temperatures. And then we can use this value and use it as initial guess for the cubic equation of the states. So now the reaching the true value, the phase change is faster than before, right? Because I have good initial guess. Also, this equation has some assumptions, but there is no kind of experimental work in it. It's not an empirical model. It's based on theoretical model, and we did some assumptions to reach it. There is another model, and I'm sure all of you read about it. That's widely used. It's the one-to-one equation. I think all of you read about it. It's a semi-empirical model. It's based on this idea, and it has the formula. Then we said A minus B with C plus D. So we get A, B, C at different. We do a lot of experiments and get the constants A, B, C for different materials, and then we can predict the saturation pressure as function of temperature. But now we need to do a lot of experiments. In this case, we need only one point. But this is semi-empirical model. You can see the same correlation: lim P sat and T, lim P sat and T. They are close. But this is theoretical with some approximations, and this is semi-empirical. Any questions? Okay. So we will talk now about first and second order So what's the difference between one phase and another? So when we can say this is a different phase of the same material. So for example, vapor, water, liquid and gas and vapor. What's the difference between them? There are a lot of differences, but one of the differences is the density, right? Density is different from the vapor and the liquid phase. Entropy from one phase and another phase is different. But this is the case for all fluids. I mean, if I found different densities and different entropy, I should call this phase change. If I didn't find this, I cannot describe it as a phase change. What's the criteria that I can use as a phase change? And this is what we discussed under this line. So for first order phase transition, we have like the Gibbs function is a continuum. Right? Gibbs function. There is a plot. Okay, plot again. So we have this G, this temperature. So at high temperature we have gas. So lower Gibbs, more stable phase. This should be gas or vapor. This one and this one is vapor. So the more, let's think we started from here. A state that's liquid for heat. I want to move with this line is the Gibbs of the liquid itself. When I increase the temperature, the Gibbs it changes as well, right? But the Gibbs of the vapor phase do change as well as a function of temperature. At some point, the Gibbs of the vapor would be lower than the Gibbs of the liquid, and this is the P set. This is where the phase change will take place. But you can see the Gibbs function itself of the whole fluid is continuous. We don't have this kind of discontinuity like the vapor, right? Like the volume. This is V, this is P. This will be liquid. This is V vapor. There is a jump here between V liquid and V vapor, right? But for the Gibbs function itself, it's continuous, right? So we will define the Gibbs function, the first order phase transition, as the phase transition that will happen and keep Gibbs function continuous, which should be the case, but the first derivative is not continuous. This is the entropy. So for first order phase transition, we have Gibbs continuous, volume is not for density in this case, and entropy they are not continuous. So they have, partial G, partial T, this is negative entropy. If you take the slope from this direction, it's different from the slope from this direction, right? So this is the first order phase transition. And accordingly, any higher derivatives are not continuous as well, right? If I take the second derivative again, partial by partial T, again, it's not continuous as well, because there is a discontinuity at this point of phase change. So for the second order phase transitions, second order phase transitions, we have the first order derivatives, they are continuous. So you can have, and you can still have phase change. So you have the Gibbs function is continuous, like this, and you can have the derivative, the first derivatives like V or S, they can be continuous as well. They can be the same in both phases. This happens mainly in the rearrangement. And there's another example, it's the magnetic. So and we call them phase change because the second derivative, of this derivative, partial 2G, partial T squared, this is partial by partial T, partial T, partial T, negative S, constant P, this is negative CT over T. this is different for the two fields that we will have. So the first derivative is continuous in this kind of phase transition, but the second derivative is not. So that's why we will call it a phase transition. Though we will have the same density, we will have the same entropy. So it's different, what kind of phase transitions we can trigger. And higher derivatives, I mean, no one ever observed higher order of phase transitions higher than the second one. No one ever observed it. So whether, I mean, in chemical engineering applications, most of the applications we will use the first order phase transitions. But in the metallurgy specifically, we will have this kind of phase transition. It happens regularly. If you do a dialectic phase transition, there is something like this in the metallurgy.
Is the diamond rearrangement?
Is it what?
Diamond rearrangement.
What?
The first line.
Rearrangement, diamond.
Diamond.
It's wrong, I don't know. Maybe not. Okay, now we can move to fugacity. Or at least everything. So how many of you heard the term fugacity before? Okay, like half of you. So fugacity, now we can calculate the phase equilibrium of pure component, right? We don't need the fugacity for any kind of complications, right? We don't need it. So where are we going to define it and make things more complicated? Actually, the definition of fugacity is more important for multi-component systems. For multi-component systems, and we didn't introduce the multi-component behavior yet, but there is something called GXS. You will define a couple. I mean, Mike will define a couple of lectures. And GXS it's the Gibbs of a mixture. It's related to the Gibbs of a mixture. And the derivative of Gibbs as function of number fraction, for example, if I have water ethanol mixture at very diluted concentration of water, I can have a slope. This slope can be very steep. It can reach infinite, negative infinity. So dealing with GXS, while this kind of discontinuity of the derivative can take place is annoying for us. We deal usually with thermodynamic continuous smooth functions, right? Because we can rearrange the derivative, make dt, we can substitute them. ddt is the same as dt, right? Only if it's a smooth continuous differentiable function. Right? So if we have this kind of discontinuity, it's annoying for us. Also, we can have the magnitude of gaps between the liquid phase and gas phase while we are doing the calculation. It can be, the magnitudes can be huge between the two phases. It can be, for example, 1, 3 for one phase and 10,000, 20,000 for different phases. So the magnitude is different between the two phases when we are doing the equilibrium calculations. So why this varies for the multi-component system? It's like, think about it if I have, this is ethanol, for example, and I'm adding only one molecule of water. Only one molecule. So the Gibbs, we know Gibbs is H minus D. The kind of entropy the new one molecule is feeling in this sea of ethanol is huge, MNS. So that's why the function can reach huge values at infinite dilution. We hold this as H is 0. That's why we need to figure out a new function that can help us solve this kind of problem. We will define fugacity based on that. Okay. So we will start with the DG function, and we know ddt minus sdt, right? Combine first and second law. If I want to calculate the change from one state, state 1, T1, P1, this is G1. If I want to move into state 2, this is real fluid. This is real fluid. No assumptions, nothing. And this equation mean there is no kind of, there is no assumptions here, right? This is the equation from combined first and second. And then I want to move into P2, P2. This is G2. So we have dg, which is G2, G, D1, D2 minus G, D, because T is the same, this term will be like crossed. This is equal to integral B dB from B1 to this is for real fluid, no assumptions, nothing. I will quote it. I will do the same thing, but not for real fluid. I will do it for an ideal gas. So we have here 1, let's call this 1 dash, let's call this 2 dash. I have T1, B1, G1, D2, B2, D2. But this time this is ideal gas. Okay? I will do exactly the same. So G by ideal gas. T1, P2, minus G, ideal gas. T1, P1, B equal to VDP will be known as ideal gases, or T over P, dB. And this is from P1 to P2. Okay? I will call this P. Then I will subtract P from N. Subtract P from A. Okay. Then I have G, T1, E2 minus D, ideal gas, T1, E2 minus T1, P1 minus P, ideal gas, T1, P1 should be equal to P1, P2, B minus 4T over P. This is E. Okay, I did nothing. I've just put the dG for real fluid, dG for ideal gas, subtracted both from each other. Nothing till now, right? So I will assume P1, that P1 is 0. So what happens for a real fluid when the pressure is 0? It's an ideal gas, right? So if I have a real fluid and make the pressure be 0, it's an ideal gas. Anything at B equals 0 is an ideal gas. Anything at volume equal infinity is an ideal gas. Right? This is the main assumption of an ideal gas. So when I make the pressure P1 is 0, real fluid approaches ideal gas. And then this term in G, T1, P2 would be equal to G ideal gas, T1, P2, P1, sorry, only as P1 goes to 0. Wow, where is this one? rewrite this one. Why do I need this? G for ideal gas is equal to G free fluid at P equals 0. So I have G free fluid at T1 T2 minus G for ideal gas at T1 P2. And this is equal to, because this then would cancel, the integral V minus R T over P dP. But this pressure now is not zero, it's 0, right? And this is P2, which I can call P because there is only one P now, right? I would just be with this one. This is T1, only B, only R. Any questions? So what do you call this? What do you call this? When I have a state function subtracting an ideal gas function from a state function, what do you call this? Departure function, right? You never heard this term before? Okay. It's in your homework. It's that's the program in your homework, I think. We nearly don't use Vanderbilt. It's a departure function. So yeah, now we can define the fugacity based on this. So fugacity is defined. So this is defined. We are defining it. It's the exponential Gp minus G square gas Gp over RT. I can rewrite it equal to P exponential V RT P. And this is the fugacity. So why this can be helpful by any means. We call it a scaled Gibbs departure function. Scaled it because we scaled it divided by RT and took the exponential multiplied with the pressure. The scaled function of the Gibbs. But this is the most important thing. The departure function from Gibbs. And we scale take the exponential because when it goes to like negative infinity or infinity, the then of this bed you can reach it is level. And the magnitude reduces when you take the length out. So we will prove next. Let's define the fugacity coefficient. It's over B. We call it the fugacity. Yes?
So the first expression of the fugacity equal to second?
What is the first one?
This is divided by RT, so what is the RT?
No, it's a different. I forgot that. I'm sorry. I'm sorry. Yeah, there is one over RT outside of the fact. So if I'm dealing with real gas, with an ideal gas, usually the fugacity coefficient is 1. Right? This integral will go to 0, exponential 0 is 1, and we will find the fugacity coefficient of 1, which then, yeah.
What is that? Fugacity equal to P by P?
This is the fugacity coefficient. It's a definition. I'm defining it again.
And that is fugacity.
Fugacity, yeah. Okay. Yeah, it's there. And I'm going handwriting is terrible. So I will erase this one. So we did nothing. I mean, we started from Gibbs difference for an ideal gas, Gibbs difference for a fluid, subtracted each other. Then we got the Gibbs departure function, scaled it, and we defined this one as the fugacity. This is the definition. We defined it because it will help us as the multi-component equilibrium. Now I want to conclude that the fugacity is also same for phases at equilibrium. So energy from the definition of fugacity, and the resistance is easy, so I will go through it for the TK equals RT and F function over P. This is from the definition of fugacity. Flat equilibrium. We know Gibbs of phase 1 is equal to Gibbs in phase 2. And the ideal gas, it's the same T, same P, so this term would be cancelled. Now I have RT, then fugacity of dP over P. After to RT, let's call it 1. This is 1, this is 2. T2, P2. This is then or P2. But we know P and T is the same at equilibrium, right? T1 is the same as T2, P1 is the same as P2. So the only, for this equality to be valid, the only thing that's needed is fugacity. Phase 1 should be equal to fugacity at phase 2. It's like the Gibbs, because it's a departure function from the Gibbs, right? If the Gibbs, it should be the same for both phases at equilibrium, fugacity should be the same as well. So how can we calculate the fugacity? This one we have less than 10 minutes. I will cover the Gibbs filter. So you remember the transformation that we did for Van der Waals equation, like to move from dP to dV? So it's easier. It's more convenient because we have P is explicit function of P. It's RT over P minus P plus A over P squared, I think. Minus. So we have P explicit in V, so it's easier if you can like directly substitute P in dV. So we'll do the same transformation here. Oh, this is the definition of fugacity. Alright. So we have then fugacity P dP equal to 1 over RT integral 0 to P B plus RT over P dP. So I will do the same transformation again. It's in your second homework, you will do it yourself. I will just remove dP, make it dP, rearrange the stuff. So I will have O 1 over RT integral from V equal to infinity. This is my gas. Instead of V equal to 0, V equal to infinity. And V equals Z, V over RT over V. And this is RT over V minus V dV. This is the integral part, and then I have another two terms, then ZV plus dV. This is the fugacity of vapor phase. This is V vapor. And fugacity So now we can calculate it, right? ZV is defined as V over RT This is V. So we have the any cubic equation of state, for example, Bain Robinson. We know P, we know V, we just solve for V in vapor. We got it, calculated ZB. This calculated from the EOS, equation of state, right? Then I have ZB here. After that, B is substituted from the cubic equation of state as well, and then you can do the integral using any calculator, your hand, anything, whatever you like. This would be new as well. But now we can calculate the fugacity of the vapor, right? And it's the same fugacity of the liquid at the saturation temperature, right? Because the fugacity is the same in the saturation temperature. Now we need to calculate the fugacity of liquid. So liquid has a problem with dV, right? We know this problem. If I want to move, this is VD. This is the cubic equation of the state. At V infinity, this is ideal gas. And we want to move into here, which is here. So we know we are going to do an integral with moving from here, jumping to here. No, this is no good. Jumping from here to here, then continue the integral. We have this continuity. So we divide the integral into 3 areas. I think Michael did the same when he got the formula for the same area condition for the physics theorem when they built the equation of state. So we define the integration into 3 parts from an ideal gas. This is one. Into a vapor. And then at the same saturation temperature, we move in liquid and moving from 2 to 3. Then moving the liquid, that's saturated here to any pressure that you want. So we have from 1 to 2, this is ideal gas, vapor, this is real vapor. And from 2 to 3, this is phase change. And from 3 to 4, saturated liquid into the pressure. So which is there 0?
What did you say?
Which step is 0?
2 to 3.
2 to 3, right. Right. Because there is no change in fugacity in the phase change, right? It's the same fugacity of the vapor, it's the same fugacity in the liquid. So we cancel this step. So we'll do the first and third step. So it's integral from P equal to 0, P equals that. V minus RT over P, dP plus third step from P set to P desired. V minus RT over P, dP. This is a gas step, right? This is similar to this one. So, this term is like the gas term exactly. We would go for RT, then fugacity saturated, dP over P. So this term, from the definition of fugacity. I just followed this exactly. It is nothing. And this time I will partially integrate it. So it's integral of P dt, P sat, P this term here, minus R P of P dt, P sat, dP. So this term is done, right? We have RT, then P sat over P. I combine everything.
Should be positive.
Which one?
This term.
No, it's I changed it.
Maybe you change it.
Yeah. let's keep it as the notes. E set. And this is B. Okay. So combining everything. So we have R, T, then Fugacity equal to B equal R, T, then Fugacity B. This is saturated. Minus R, T, then B reversed plus techno B B. We will just do some mathematical tricks, and for the time's sake, I just write the final formula for the Fugacity for liquid. I mean, if you have time, I can show it to you after the lecture. So Fugacity liquid equal to Fugacity, the saturated vapor, and liquid at the same temperature. This is A and B. Multiplied by 1 over RT, integral B set, V. So what we call this term is the pointing factor. And actually we can further approximate this one. So the fugacity of the liquid is just the fugacity of the saturated vapor at the same temperature multiplied by 1. And this factor we can further simplify. We can assume that the liquid is compressible, which is reasonable, right? So V is constant at that time. We can take it out of the integration. So if this term, like exponential, would be V multiplied by B minus B. This is approximation, and the fugacity of the liquid set same D multiplied by this term. No integration here because we assumed it's incompressible. V is constant. This is the case only incompressible, which is valid also for solids, right? Same for solids. Right. We can make further approximation to this one. We can assume that the vapor phase is ideal gas, and the fugacity is close. I mean, the pressure we're operating at is P is close to the saturation pressure, which means this term would be 0, right? Exponential of 0 is 1, and then F saturated liquid, AP would be approximately equal to the saturated vapor at the same T. This is vapor, which is a saturated liquid as well. They are the same. So why do we need the fugacity at high pressure? I mean, if we're interested in phase change, why do we care about the fugacity at high pressure? Right, because we can stop at a saturation temperature. We can stop here. Why are we going to higher pressure? Because it can be important in liquid-liquid equilibrium. So the criteria for liquid-liquid equilibrium is also the fugacity of both phases. If I have a container and I separate into two phases, this is ethanol and water again. So the criteria for equilibrium is the fugacity of component I in phase 1 is equal to the fugacity component I in phase 2. The fugacity of ethanol in the ethanol-rich phase should be equal to the fugacity of ethanol in the ethanol-rich phase. And this liquid-liquid equilibrium can take place at higher pressure than the saturation temperature. So we can calculate the fugacity based on this one, based on this correlation. I'm late 5 minutes. But if you have any questions, we can discuss them after the lecture. I know you are the approved lecture. And thank you.